Hello everybody, myself Jyoti and this is sixth lecture on nuclear energy, and today specifically we are going to study neutron cycle in a thermal nuclear reactor, which is more commonly called as four-factor formula, and this is very important topic. So first of all, what is neutron cycle? The neutron cycle or chain reaction in a thermal reactor can be described in terms of a cycle that shows what happens to the neutrons. So we will study this cycle stepwise. What happens in the first step, second step, third step, and that is how we will study the whole cycle or whole journey of neutron inside a nuclear reactor. So step 1. Now this neutron cycle is very important. You may find it a little difficult, but it is very easy. So first step. So we will start with the fission reaction of uranium-238. So we know that uranium-235. Uranium-235, it undergoes fission with thermal neutron. So we have thermal neutron, slow neutron and fast neutron. If we want nuclear fission of uranium-235, then we need a thermal neutron. Thermal neutron, in a sense, the energy of the neutron, it shouldn't be very high. It should be in a certain range where it can cause the nuclear fission of uranium-235. Now, when we have seen in earlier lectures nuclear fission of uranium-235, it captures a neutron, it forms the fission fragments barium and krypton, and along with it approximately 3 neutrons are emitted. Now suppose here, for simplicity, that we consider that uranium-235 nucleus, it captures a neutron and it produces new fast neutrons. Whenever we talk about nuclear fission reaction, the neutrons which are emitted during nuclear fission, they are fast neutrons, or they are called as prompt neutrons. And the neutron which is required for fission of uranium-235, it is not a fast neutron, it is thermal neutron. Okay, so keep this in mind. Now these neutrons, new fast neutrons which are emitted, they have an average energy above the fission threshold for uranium-238. That means, as we have said, that thermal neutrons can cause fission of uranium-235, in a similar way, fast neutrons, they are capable of causing nuclear fission of uranium-238, and some of the new fast neutrons which are emitted in nuclear fission reaction, they cause the fission of uranium-238 nucleus. Now the chance for such additional fissions, it depends whether the fission neutron can collide with uranium-238 nuclei before colliding with moderator atoms. Because these new fast neutrons are emitted, they may collide with moderator, they may collide with uranium-238. If they collide with uranium-238, as they have higher energy above the fission threshold for uranium-238, they can cause the fission of uranium-238. But suppose they collide with the moderator atoms, if they will collide with the moderator atoms, their energy will become less and they will become thermal neutrons from fast neutrons. So a small fraction of the neutrons that do collide with uranium-238 nuclei cause fission, and we know that during nuclear fission neutrons are emitted. So uranium-238, when it undergoes nuclear fission, that time also some fast neutrons are emitted. So पहले uranium-235 का nuclear fission हुआ, it emitted neutrons. Then uranium-238 underwent fission reaction, it also emitted fast neutrons. So now the total number of fast neutrons from fission is increased from nu to nu epsilon, where epsilon, it is a quantity which may be equal to 1 or greater than unity, and this quantity epsilon is called the fast fission factor. Now what happens next? Now as the nu epsilon, so we have now nu epsilons, neutrons pass through the reactor and most of them are slowed down, but a fraction LF escapes before being slowed down to thermal energies. We have now nu epsilon, neutrons, which are fast neutrons. So some of them may be slowed down with the help of moderator, but some of them may not. They escape slowing down process. So that fraction LF, it is called as leakage factor for fast neutrons. fast neutrons which are escaped from being slowed down. Therefore, a total of nu epsilon LF escape. Earlier we had nu epsilon. LF is the leakage factor for fast neutrons. So nu epsilon into LF, it escapes or they get lost as far as chain reaction is concerned. And what will be the remaining, because LF, it stands for probability. So if LF neutrons, they are escaping, we will have 1 minus LF which are remaining. So that is how the probability works. So the remaining nu epsilon 1 minus LF neutrons are slowed down by collision with moderator atoms. What happens next? But during the slowing down process, some of them may be captured by uranium-238. If the slow neutrons, they are captured by uranium-238, then they form uranium-239, which decays to Neptunium-239 and then to plutonium-239. Just remember here, earlier also the neutron was captured by uranium-238, but that was fast neutron and that caused the fission of uranium-238. But now this neutron, it is thermal neutron. So if thermal neutron is captured by uranium-238, it cannot cause fission of uranium-238. It forms uranium-239 which decays to Neptunium-239 and then to plutonium-239. This capture process is called as a resonance reaction. So out of nu epsilon 1 minus LF neutrons which start slowing down the process, a fraction escapes resonance capture. That fraction is nu epsilon 1 minus LF into P. While the fraction nu epsilon 1 minus LF 1 minus P is captured and goes to form plutonium-239. So the quantity P here, it is called as resonance escape probability. Now the absorbed neutrons cannot cause further fission of uranium-235 and are lost. Now what next? The neutrons which escape from resonance absorption, that is nu epsilon 1 minus LF into P, they are slowed down with the help of moderator to thermal energies, where two processes are possible. First process is some of the neutrons diffuse. They are going out of the reaction. Some of the neutrons diffuse without being captured and eventually escape from the system. And if the fraction escaping, we denote it by LT. Now this LT, it is called as leakage factor for thermal neutrons, because now the neutrons, they have already passed through moderator atoms, and from fast neutrons they have become thermal neutrons. So LT, and now these thermal neutrons are escaping, so that is LT, leakage factor for thermal neutrons. The number of thermal neutrons per fission of uranium-235 escape, it is equals to nu epsilon 1 minus LF P into LT. So how much is remaining? Nu epsilon 1 minus LF P 1 minus LT are remaining. So now this remaining thermal neutrons, a fraction F is absorbed in uranium and the fraction 1 minus F is absorbed in other materials. Other materials में क्या आ जाएगा? Moderator and nuclear reactor में wall of the nuclear reactor and so on. So these neutrons are lost to other materials. The number of neutrons still which are available for carrying on chain reaction is then nu epsilon 1 minus LF P 1 minus LT into EF. Now this F is called as thermal utilization factor. Thermal utilization factor in the sense still this many neutrons, they can cause the fission of uranium-235. Now not all of the neutrons, one more thing. Now we have this many neutrons which can cause nuclear fission of uranium-235, but not all of them, they absorbed in uranium and cause fission of uranium-235. Though they are absorbed by uranium-235, some of them may not cause fission of uranium-235. Some of the neutrons are absorbed by uranium-238 to form uranium-239 eventually, which will form plutonium-239, while what is the fraction which is remaining now? Nu epsilon 1 minus LF P 1 minus LT into Fg. They are absorbing uranium-235 to form uranium-236, now which is unstable. So the number of second generation fissions in uranium-235 per fission of uranium-235 by a first generation neutron, that is called as the reproduction factor or multiplication factor and is denoted by K. Like suppose in the first generation, I have the uranium 235, it utilizes one neutron and it suppose produces three neutrons. So in that case, K will be 3 upon 1, that is 3. That way you have to calculate the reproduction factor or multiplication factor. Or suppose from the 3 neutrons, initially I have 3 neutrons and I got 27 neutrons. So 27 by 3, that will give me the reproduction factor or multiplication factor. So, K I can write as number of neutrons in n plus 1th generation upon number of neutrons in nth generation. So K, it will be nu epsilon 1 minus LF P 1 minus LT sigma F of u upon sigma A of u. Now nu multiplied by sigma F of u upon sigma F of u, sigma A of u, it represents nothing but the number of fast fission neutrons produced per thermal neutron absorbed in uranium, because we know that nu were the initial fast neutrons which were emitted, and sigma F of u upon sigma F of A of u gives you how many neutrons were utilized for fast fission and how many neutrons were absorbed for fission reaction and how many neutrons were absorbed without producing fission reaction. So nu into sigma F of u upon sigma A of u, it gives you basically the number of fast fission neutrons produced per thermal neutron absorbed in uranium, and this can be written as eta. So I get the formula for K as eta epsilon P F 1 minus LF into 1 minus LT, and here this quantity K, it is called as the effective multiplication factor. Now this K, which we call as the effective multiplication factor, it is very very important in reactor physics and it determines the functioning of a reactor. So if K is equals to 1, K equals to 1 means my chain reactant system, it is operating in a steady state. That means whatever number of neutrons are utilized for producing fission, same number of neutrons I am getting at the end. Suppose 1 neutron I have used for fission, then at the end I am getting 1 neutron only. So that way the system will be in a steady state. And here the chain reactant system or the nuclear reactor system, it is said to be in a critical state, or the size of the chain reacting system we call as a critical size. If K less than 1, K less than 1, that means there is no chain reaction. K less than 1 means the reacting system or nuclear reactor, it is said to be in a subcritical state. It signifies a convergent state where number of neutrons produced per fission, they go on reducing. Suppose initially I have started with 3 neutrons but I get only 2 neutrons. If I use 2 neutrons, at the end I am not getting any neutron that way. So the number of neutrons or fissions and energy output diminish from one cycle to the next cycle, and then the reactor, we can say that the reactor is quenched. What happens when K greater than 1? If K greater than 1, the number of neutrons and fissions increases from cycle to cycle. Suppose I have utilized 1 neutron, at the end I am going to get more than 1. If I have used 5 neutrons, at the end I am going to get more than 5 neutrons. So number of fission increase from cycle to cycle. So from 1 I'll get 3 neutrons, from 3 I'll get 9, from 9 I'll get 27, that way. And the chain reaction is said to be in divergent state. And the size of the chain reacting system, it is called as supercritical state. Now, if the system is infinitely large, there is no leakage of neutrons from such a system. That is, leakage of neutrons, it is not possible. And then the leakage factor for fast neutrons and leakage factor for thermal neutrons, LF and LT, we can take both as 0. And if we take both as 0, the formula for K, it becomes K equals to eta epsilon PF. And here the K we will denote as K infinity, and now the name is multiplication factor. This formula K infinity equals to eta epsilon PF, this is called as the 4-factor formula. So if you want to summarize everything with a simple image, this is the way. So we have uranium 235 which undergoes fission reaction, it gives fission fragments and it produces new fast neutrons. One of the fast neutrons, suppose it interacts with the uranium 238 nucleus, it produces fission fragments, and that will also produce fission reaction of uranium 238. It will also produce some neutrons. So total neutrons which are produced here are nu epsilon fast neutrons. This nu epsilon fast, out of this nu epsilon fast neutrons, some may escape the resonance reaction. The factor for it is, suppose, LF, leakage factor for fast neutrons. So how many neutrons are left? Nu epsilon 1 minus LF fast neutrons are left, which will pass through the moderator, and some of the neutrons, they are captured by the uranium 238 to form uranium 239, and this reaction is called as resonance absorption reaction. The uranium 239 which is formed here decays to neptunium 239 and then to plutonium 239. The moderator atoms, when the fast neutrons they pass through moderator, suppose we have now nu epsilon 1 minus LF into p neutrons which are left. Now this neutrons are now slow neutrons. Some of the neutrons, some of the thermal neutrons may escape. So suppose LT, it is the leakage factor. So we have nu epsilon 1 minus LF P LT neutrons which escape. So how many neutrons are left? Nu epsilon 1 minus LF P 1 minus LT and F neutrons. Slow neutrons are left. Out of that, suppose nu epsilon 1 minus LF P 1 minus LT F into 1 minus G. These many slow neutrons absorb in uranium 238 to form uranium 239, which decays to neptunium 239 and then to plutonium 239. And slow neutrons which cause fission of uranium 235, that will be now nu epsilon 1 minus LF P 1 minus LT F into G. So this is how the summary, you can summarize the different steps which I have already discussed for the neutron cycle inside a nuclear reactor. So thank you so much.